Okay, my wonderful students, this is the last lecture before exam 3, so everything that we talk about today is going to be on exam 3, and actually, today we're going to be talking about parallax again, which was a topic from exam 1. So, as I've said before, it's not supposed to be cumulative midterms, but sometimes it ends up being a lot of stuff to recall. So I want to first of all ask you a clicker question, just yes or no. How many of you made it to the observatory last night? Okay. Cole, you on? Okay. By the way, you guys in the back, you guys in the back on that right side of the room that I'm pointing to. You guys back there, you might not be getting your clicks in. We tested out in the corner over there. You might want to move forward or over here to the right if you want to get your clicks in. It works pretty well from the back corner over here. So if you do want to sit in the bad boy row, sit in the bad boy row back over here. All right. But yeah, move forward a little bit if you want to. Okay, everybody voted. 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, it looks like we had about 55 on there. Daniel, were you going to ask me a question?
Yeah, about when the points will be posted on web courses.
Okay, the points on web courses for the bonus points from Observatory. Daniel's asking me, Dr. B, when are you going to get those points up? I do not have the handout from last week or from last night. And sometimes it takes a couple weeks because those guys are undergraduates, most of them. And as busy as you are, just think about how busy they are. Okay, and what they're doing is volunteering. So sometimes it takes them a while to get it all sorted out. And, you know, sorting papers like that, especially deciphering your guys' messy handwriting, can be kind of tricky. And so sometimes it takes a while, but we'll get it, and it'll go in there, you know, pretty much the same day that I get it, if I'm on campus anyways, I put it in, you know, 'cause all right. Now, I want to go to the, can you switch to the computer now, please? All right. I want to show you a video here on the screen of a train. And I want you to listen carefully. Go ahead and start playing this. Now listen to when the train comes around the bend, it'll blow its horn. Okay? Yeah, get rid of that stuff. Here it comes. And about 40 seconds in, did you hear that? Let's try that. Back that up to about 30 seconds. 30-something seconds. Okay, good. What did you notice about the sound of the train horn? Well, huh?
It echoes.
Yeah, you're getting echoes and it's noisy and stuff, but
Changes as it goes by.
what changes?
The sound, like the way that it sounds.
Oh, it's louder?
Sure, but it's like then I don't. Like,
How do you-
it goes off, I guess.
How do you what somebody over here was saying something. What's that? Yeah, the pitch. The pitch change. Let's listen to it one more time. That's good. Listen to the change in the pitch. Hear that? The pitch starts up high as it's moving towards you. Switch over to laptop, please. And then it dips. It kind of goes as it goes. I can't really do it very good, but as it goes past you. Now, that is a significant thing for us. That's called the Doppler shift. All right? And here's the, if you want to jot down the YouTube address, this change of pitch, we're actually going to use it, the Doppler shift for electromagnetic radiation to study starlight. But it's nice to think about it in terms of sound wave Doppler shifts. So that change of pitch is at about 40 seconds in this video. And all you got to do is type in rail fan in YouTube and you'll get buku. I mean, it's kind of cool actually if you like trains, you know, to listen to the trains. But you gotta listen sometimes for a few minutes before you catch a Doppler shift. So it's higher pitch when it's approaching the rail fan, the observer. But then after it passes and now it's moving away from him on down the track, the pitch is lowered when it's receding from the observer. Now, that's all relative to the sound or the pitch that that train would have if the observer, the rail fan, was at rest with respect to the train. So in other words, if the train was in the freight yard and just standing still, getting ready to go, and he goes, like you do, you go like this, and the truck driver, the rail, the engineer will blow his horn, so if he goes like this, and he's in the train yard and nobody's moving, then he'll hear kind of a medium pitch. And the pitch that he hears and that you heard as the train approaching was a little bit higher than that. And then as the train passed him by, it went down and that pitch was a little bit lower, all right, than the normal stationary observer, stationary train sound, all right? Now, that is similar to the Doppler shift for electromagnetic radiation. And what we find is that spectral lines, for instance, will shift. So, and as we did on the first day of class, the spectral lines of hydrogen, for instance, H alpha, you might find that if the star or even the planet or the spacecraft, really, I mean, if you bounce something off a spacecraft and it returns to you, if the spacecraft is coming towards you, like the train was, it'll come back with a different color. That spectral line will be shifted toward the blue. Now, you can't hear electromagnetic radiation, but you can see it. That's how we sense it. All right? So if you're looking at H alpha, it might look a little more towards the blue. Now, if it's moving away from you, you might see it as the spectral line shifting toward the red. Now, let's talk about H alpha. All right, so just as an example, and H alpha is one of the most common lines that astronomers look at because there's so much hydrogen in the universe. And that beautiful red H alpha line is really easy to spot, okay? No matter pretty much anywhere there's hydrogen, so in other words, anywhere in the universe, visible matter, you're going to see a lot of hydrogen. You're going to, in many conditions, not all conditions, you'll see H alpha. Now, if that source, that star, is moving away from you, you'll get a red shift. So it might look deeper in the reds. H alpha is a red, but it's not the longest wavelength of the reds. So it's the wavelength of H alpha is 656 nanometers. All right, so if you shifted another 44, you'll be at 700, and that's about the longest, supposedly, red that humans can see. You know, humans, we can see from about 400 nanometer wavelength violet to 700 nanometer wavelength red. Maybe a few of you guys, you know, then they say that bees can see infrared and various other animals can see a little bit of infrared. And you might see a little bit longer than 700. And some of you might only see like the 695 or something like that. But the rule of thumb is 700 and 400. Okay, so a blue shift, if the planet is coming towards you or the star is moving towards you, or if a part of the star is coming towards you, it might not be blue, but it might be shifted in that direction. In other words, from R up towards the V part of Roy G. Biv. So it might shift into the orange. And sometimes we look at galaxies. We look at entire galaxies, and we'll be talking about galaxies in 2 weeks during Black Holes Week, last full week of the semester. We'll be talking about galaxies, and we can sometimes see really profound red shifts because all the galaxies in the universe, except for Andromeda and a couple of little close by ones, but everything, you know, fairly far away from us is expanding away from us. The universe itself is expanding. So everything is moving away from each other. And we know that because it's all redshifted. The H alphas, the helium lines, the neon, any line that you see, when you get that quantum fingerprint, you say, I got hydrogen, but it's redshifted. And some of the most distant galaxies have the deepest redshift, sometimes into infrared. So it's, anyways, we're going to be talking about Doppler shift today in our class. Now, before we go any further, I want to do kind of a little mini review, actually, for the test. I want you to think visually about these two Dipsy isotope ratios that we've been talking about out the wazoo, delta 17 and delta 18. And I'm going to give you a look at it. Now, I'm using a special resolution today. I'm using actually 1080p. That's 1920 pixels by 1080 pixels height. So 1080p is going to allow me to draw a rectangle now that has 1 million pixels. And you might say to yourself, Dr. B, why are you talking about 1 million pixels? Well, the reason is SMOW, delta 17, delta 18, we usually rate those in parts per million. Right? So I'm going to make something with 1 million pieces. Here it is. That's 1 million pixels in HD, 1080p. All right, so this rectangle, go ahead and make a rectangle of those proportions. And this part of the lecture, you can actually, the proportions are simple enough that you know, hopefully you can get this done. So this one's 1250 pixels wide, 800 pixels tall. All right, so all four corners. In other words, it's 1 million pixels. All right. Now, what we're going to do is consider that to be our sample. And then what we're going to do is simulate SMOW inside this 1 million pixels. All right. So what we want to do is get 380 of the pixels for delta 17 and about 2005 pixels out of this 1 million for delta 18 and for SMOW. And I've got NWA 3003 up there too. It's also pretty close to SMOW, although measurably different. Now, you may think to yourself, Dr. B, what's that little red square? Ah! Brr. Where's my cursor? There we go. What's this little thing over here? That is actually 1 pixel surrounded by a 10 pixel by 10 pixel square. Now, I don't think you can write this in, but I'm going to blow it up for you. Now, watch. I want you to have your eyeballs up here. All right? Eyeballs up here. Come on. Look at this. All right? So that red box is 10 pixels by 10 pixels. You can't see the 1 pixel at the center of it. Now, I'm going to blow it up by 400%. All right, there it is. Now you can see that. Can you guys in the back see that little blue pixel in the middle? All right. All right, now I'm going to bring it back down to normal size. All right, now here we go. Let me get this out of the way. Here is a rectangle for delta 18. Right there it is. Now don't draw it in yet. It's long, slender. It's 2005 pixels. I'm going to move it over here, and now you can kind of draw it in over there. All right. It's 5 by 401. Okay, that's 2005 pixels. All right. So in a million oxygens from SMOW, you know, typical million gallons of water or typical gallon of water from the briny deep, that's the fraction that have oxygen 18. Right? Now that's a rectangle. Now we're going to do oxygen 17 now. Okay, now the abundance for that is 379.9. So I'm going to round that off to 380. All right, here it is. Ding. It's kind of, just move it up here. And yeah, 38 by 10. Rectangle up there. It's, you know, I don't know. Maybe I was wrong about making a sketch of this. Try to draw on something slivery. You know, I made the delta 17 horizontal and the delta 18 vertical. And I could have made a slightly different size for the delta 18 so it looks a little, you know, delta 17 you can actually see it. Delta 18 over there on the right, it looks just like a line over there. It's still pretty, it's only 5 pixels across. So it's still kind of pokey. But try to sketch that in. All right. And that's what we're talking about. The abundance of oxygen 18, the abundance of oxygen 17 in the oceans of Earth is, you know, represented here by those 2 teeny little slivers. And everything else in there, all the blue pixels in that big rectangle, that's good old oxygen 16. All right, so this gives you a visual handle on it. Now, I want to go ahead and make yourself another rectangle. I want to try circles. All right, and the circles, you know, I was looking at those rectangles last night, and I thought, let's try circles. Now, circles are trickier because you can't get an exact whole number of pixels. All right, so let's try to do some pixel action here. All right. Now here, I've got it over here. Oh, let me get my cursor over there. This drives me nuts. I'm trying to do this backwards, upside out. All right, so here's my oxygen 18. That looks a little bit nicer. So that's taking that long slivery one that we just did, 401 tall, 5 units across, and balling it up into a circle. All right, so here it is. Let me move it over. Uh-oh, it disappeared. Hold on a second. I can fix that. Let me get my cursor back. This is a catastrophe. Where the heck is it? Here it is. Okay, there it is. Okay, that you can sketch in. So sketch in, you know, this is 1080p, so it's 16 across 9, it's ratio 16 to 9, width to height. And that circle you can definitely draw in, okay, over there on the right. So that's approximately a circle of approximately 25.26 pixel radius, all right? And it's kind of hard to do, but I managed to do that. Now, let's do oxygen 17. All right, now this one, here it comes. All right, there it is, right over here, okay? And let's just park that over here. That's a little easier to draw too. All right, so try to draw those in. All right, now that's SMOW. NWA 3003 from the homework is going to be fairly close to that. As you can see, the numbers are the abundances are pretty close. But we can even distinguish between those two sets of circles if we had to. Right, so this is 380 pixels over there, 11 pixel circle for, or 11 pixel radius for oxygen 17. Now, I have a clicker question for you, multiple choice. And by way of reviewing in your mind, think back to McKeegan. Wait a minute. Let me get my cursor back here. My goodness. See if you can go ahead and switch back. All right. Is McKeegan going to have a bigger, smaller, identical, or zero radius circle compared to what we just saw for SMOW? Remember? Go ahead and vote. Yeah. Okay, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Yeah, okay, most of you got this one right because I have the answer pointed out to you. So look at this answer. I'm sorry, I forgot to animate it. That red dot here, there's the hot spot. And we call it a hot spot. It's loaded with oxygen 17. It's even above 800 if I recall correctly. All right, so it's red. All right, so that means it's above. So delta 17 is positive. So that means 800 pixels or more. And figure out whatever the abundance is. And matter of fact, let's take a look at McKeegan. All right, now draw yourself another rectangle. And let's draw in McKeegan. So here's another column for that table, right, in yellow. So McKeegan is 1010 parts per million for oxygen 17, and it's actually a little depleted in oxygen 18. It's down to 1770. That's all right. So that one would plot up as a smaller circle, but oxygen 17 definitely bigger. All right, so here's the oxygen 18 circle, and it's, go ahead and draw one over there, try to make it look at about the same proportion, and it's actually a little bit smaller. Let the numbers do the talking. Jot down 23.74. Okay, that's the radius in pixels for this circle, and that gives you about 1770 pixels, you know, pi r squared for the area. All right, now here comes oxygen 17. All right, there it is. And it is pretty big compared to the other one. All right, now here it is. 1010 pixels. And my wonderful students, that is definitely bigger. Now, if you don't believe me, here they are. Let me get these in there for you. Now, remember, this big, relatively big circle for oxygen 17 is the sign that it came from a red giant star, and that's what we're talking about today in lecture, the classification of stars. All right, so here's the delta 17 for SMOW. The red one down there, That's SMOW, the red one with the white border. And the white one with the red border is visibly bigger. All right. Now you still have to be pretty precise to catch these. So you have to do a good job of analyzing in the chemistry lab. But yeah, that's it. All right. So that is the sign of a red giant star. And now you have some visual proportionality to think about when you're doing those dipsy ratios. I mean, the numbers are nice, everything. But visually, this is what we're talking about. Whether you use the little rectangles or the circles or any other shape, really. All right, now, last time we talked about the idealized blackbody spectra. Here's a couple. The sun and a star called Procyon A. And it's Procyon A is a little bit brighter than the sun. And so its curve, it's the solid curve. The sun is dashed. Okay. And you can see the wavelengths there. For the SUN, the wavelength is, 50 something? And then and that's for a 5800 Kelvin star. And then for Procyon A, it's 430. Boy, I can't read it. 438 nanometers. Okay, so that's deep in the violets. It's almost out of the violet into the ultraviolet. All right, so Procyon A, and it's in the constellation Canis Minor, which is near Sirius and Orion. And it's a pretty bright star down there. Actually, what did you guys look at last night? Orion Nebula again? Okay. How about the moon? Anybody look at the moon?
Yeah.
So, and did you know that Saturday night is a blue moon? In other words, second full moon in the month of March. There was one at the beginning of March, and whenever there's a month on the calendar where there's two full moons, which happens every once in a while, you call the second one the blue moon. I don't know why, but that's what they call it. Anyway, so Procyon A is near Orion and Sirius. Now, these shapes, they're controlled by quantum physics. Now, we're not going to go into the quantum physics of these blackbody spectra, but the one factor that controls the shape and the height, where the peak is and how high it is above, like above the sun's or below the sun's spectrum, is the surface temperature. All right? And here's the formula that we calculated with last time. Lambda max, that's the peak wavelength. And you could do a similar calculation with the peak frequency, but usually wavelength is a little bit easier to work with. Lambda max, peak wavelength, times temperature in the Kelvin scale equals 0.002898 meter Kelvin. And we did some and we're going to do another calculation here in a minute. All right. Matter of fact, we're going to go over the calculation that we did at the end of class. All right. This temperature also gives it a distinctive color. So you might say something is red if its peak wavelength is down in the 600s. Or you might say something is blue if it's or down in the 450s or so, right? And green is going to be, like maybe 550 or so. Green's kind of in the middle, right? And our star is actually kind of green. Right now, some of the examples that we did or that we talked about, the sun, 5800 Kelvin. And that's, and actually I was looking at the solar spec sheet last night. I was working out some calculations. And what NASA says is that it's 5778, which is pretty close to, if you round it up, that's 5800. Right? Betelgeuse, a red supergiant in Orion that you were looking at last night, Yeah, Betelgeuse. Red supergiant. Yeah. So a star, maybe a little bit smaller, a red giant star, gave us that particle in McKeegan, that pre-solar grain that they picked up. Temperature on the surface of Orion is 3590. Now, how do we know it's a red supergiant? How can we know that it's not? I mean, Betelgeuse is pretty bright, so what if it? How do we know that it's giant and not a small red star, just really close? Well, the reason we know that is we can work out all the numbers and stuff, and if we can get a parallax measurement to Betelgeuse, then we know the distance. So we know, okay, it really is something real. It's far enough away that it's still so bright, and even though it's way far away, many parsecs away, but it's still really bright, that means it's really big. And you could do all the math and stuff and figure out its exact radius, or pretty close anyways. Procyon A, 6530 for the temperature. Now, I'm going to give you a look here at the real spectrum of the SUN. Here they are together, and I've kind of shifted them over a little bit. That orangey shape is like the spectrum of the SUN, the real spectrum of the sun, and colored in orange. Now, let's just take a look at it. All right. There it is. All right. So the sharp peaks and valleys that you see in that, those are absorption features. All right. So the real, the real spectrum of the sun, if you measure it wavelength, every 10 nanometers of wavelength, for instance, and you write down the brightness, and then you post it up, it'll have holes in it like this, bullet holes in the spectrum. But anyways, that's what this it's close to a perfect blackbody spectrum, but it's got those absorption features, bullet holes and stuff like that. Now, last time we worked on this question, 570 nanometers, which is, according to NASA, that's yellow. In the Roy G. Biv visible band. And we calculated that it corresponds to a temperature of about 5084. Now let's review that calculation. So if you were absent on Tuesday, jot it down. If you're on your calculator and you know how to use your EE button, and remember, and bring your calculator to the exam, because you cannot use your cell phone during the exam, even though a cell phone, like my iPhone, has a nice little scientific calculator with the EE button and everything. Anyways, there in the black rectangle, that'll give it to you right away. That'll give you 5084 chop chop. Now, if you're doing it on pencil and paper, you start with 0.002898 meters Kelvin divided by the wavelength, 570, and a nanometer is always a 10 to the minus 9 meter. All right, and I asked you to review your metric prefixes and suffixes. All right, so then, all right, 10 to the minus 9 in the denominator in the first equation is the same as 10 to the regular 9 in the numerator. All right, so that's my trick. I mean, you don't have to do it. You can do it on your calculator if you know what you're doing, and I suggest you practice. But I mean, if you're doing it this way, this is how I do it. I like to get all my exponents in one place. All my powers of 10 up in the numerator, just, so it's, And so, but I still have 570 underneath there. And then you do this. You calculate 0.002898 divided by 570. So now I've got a bunch of other zeros after the decimal. And then I've got 50842. And I've got 10 to the 9 out there, and I still have kelvins. And by the way, as I was working with a student yesterday, don't forget that, in the first equation block, you can cancel meters on top and meters on the bottom. because you're looking for a temperature, so you don't want meters in your answer. You just want kelvins, capital K. All right, so we've got, let me see if I can do this properly. 0.0000050,842 times 10 to the 9. Bogus. Let's just get a whole number of kelvins, because we know it's going to be, for most stars, a few thousand, maybe 10,000 or more, but not 100,000 at the surface. I'm pretty sure. Anyway, so just move, the decimal point over 9 spots, and you get to 5084. And you could drop the 10 on the 9 because you've moved the decimal point 9 spots. All right. Now, that's how you do it on pencil and paper. If you're doing it on a calculator, you get immediately 5084 point, blah de blah, and you just round it off to the nearest. And so I'll just tell you straight up right now, on Tuesday, be ready to calculate with your clicker, and you're going to be entering your question answers with your iClicker. So make sure you bring it, and make sure you're not sitting in the back row. So you got here late, and you didn't hear me say that people in the back are sometimes not getting their clicks in. Yeah, you're listening to music. You're not listening to me. Yeah, take your earbuds out. Yeah, if you're back there, I might not be getting your clicks. So don't sit there in class. Go over here and sit in the back row over here if you have to. But over there during a test is a disaster. All right. Now, let's do another calculation. Here we go. And I'll give you a couple of minutes. We'll turn the lights up. Question first. I'm going to ask you, well, the question we're about to do is a multiple choice, so you have to choose the right answer, and they're all whole numbers of kelvins. But usually, for a star surface temperature, like the sun, we usually just say 5,800, but NASA will give you a whole, the nearest single Kelvin. It's like 5778, I think is what they have. Usually we don't go into decimals of tenths. So just use the nearest whole number, which is 5084 in this one. Now, here's another one. Let's do this one. Peak temperature 501.6, or excuse me, peak wavelength 501.6. Now, go ahead and calculate this one. All right. And use a calculator or paper and pencil, either way. Usually, when I give you a multiple choice question for a calculation, I'll give you some numbers that are clearly not correct. Like 50 million Kelvin or something like that, or 0.05 Kelvin, but not on this kind. All right, so one of these is correct. So work this one out. And hopefully, you guys will do good. Can you go to 100% light? And definitely, check with your neighbor and, if you, and as I've mentioned before, it's always good to have a study partner or, a friend. And even if you live over in Rosen, there's bundles of people over. Did you know that Mr. Rosen loves astronomy? We used to teach, I don't know if they still teach over there, but every fall semester we used to have a big section of Astronomy 2002 because he loves astronomy. And he wanted all of his students to take it. So he's been a good friend of UCF. So anyways, over in Rosen, if you live over in Rosen, there's probably bunches of people over there that you could partner up with for study partners. Doing pretty good. 45 seconds starting now. Fifteen seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Let's see. 89% of you got that one right. Good. Now, on exam 3, I'm not going to tell you what's going to be on the exam, but you can make your own deductions. But be ready, either multiple choice or calculation with iClicker, typing in the actual number. Okay? And that's a little tougher. Because I don't give you any possible answers on the iClicker version of a question like this. You just got to have it right. So, and that's why they're worth more than 1 point. And it's just so you know, that's our star. 5778, yeah. That's our peak wavelength. It's kind of green. It's nice. All right. Now, the key to all this stuff, as I mentioned before, is to get a parallax measurement of the distance. And we got a bunch of we got a new satellite up there called Gaia that's bagging zillions of stars close and far away, getting a good parallax on those babies. And the reason that it's nice to get a parallax is the Stefan Boltzmann law. And this was the second formula that I want to talk about. Now, this one's a little bit tougher. It's a constant sigma times T to the fourth. So take your Kelvin temperature. So I might give you a cinchy Stefan Boltzmann question on the test. But what it tells you is capital F is the flux. Every square meter of your star surface is putting out so many watts of energy. And this is how you calculate it. And you can do this for the sun. Use 5778, square it, and then square it again. That's the fourth power. And then multiply that by sigma. Now, here's the value of sigma. Go ahead and write that down. And I might give you, in your homework this weekend, I might give you a cinchy. I gotta figure out an easy example of Stefan Boltzmann, because I don't want to burn your brains out too badly. But it's 5.67 times 10 to the minus 8 watts per square meter per Kelvin to the fourth power. So that cancels out the Kelvin to the fourth in the formula from the fourth power of the temperature. And so this is, sigma is actually a bunch of, like the speed of light, and pi is in there, and a bunch of other physical constants of nature are actually in sigma. But this is the value of it. And this applies to all star surfaces, not just the red star, Betelgeuse, Procyon A, kind of a bluish star. Yeah. You get the temperature, look at the peak wavelength, get the temperature, then get the flux, and then get a parallax, and you got it all. So this is the Stefan Boltzmann law. So I'll try to put your home. By the way, the homework, I'm going to give you another asteroid or meteorite to calculate, just for extra practice, because I know a few of you asked for more practice on that. And so I'll give you a little tiny calculation homework over the weekend. So let's review the logic now. This one, I'll give you a simple calculation. This one, again, tells you for every square meter of your astronomical object, so about a square meter is about this wide and about this tall. Okay, about this tall. A square meter is going to put out so many watts, so many joules per second. Now we can do this for the sun or any other, and actually any other object. Every other incandescent object obeys this law. Pretty close. It's not perfect, but it's pretty close. It's pretty close enough for government work. You know, so like the filament in an incandescent bulb, like the one that we looked at on the first day. And actually, I think some of these are incandescent up here. And they have a spectrum, continuous spectrum. Anyway, so here's the logic. Here we go. And these are all false color pictures of the sun. If you know the temperature, then you can calculate how much energy and actually how many photons per second get blazed off the surface of every square meter. All right, now, for a star, it's going to be really a lot of photons. And did you know that your eye is so sensitive? When you're looking at starlight, you're getting just a few dozen photons of light per second. It's very, very, it's amazing how sensitive your eyes are. You know, our visual equipment is unbelievably, and of course, our brain is the brains of the outfit. I mean, the brain, your brain ability to visually process things and make visual deductions is incredible. Anyway, so you know the temp, you know how many photons per second at the surface. All right? Now, if you know how many photons per second at the surface, and if you know the luminosity, which you can get from, you know, knowing the distance, you can figure out how many square meters of surface. So the luminosity is your basic rating of that star, knowing how far away it is. So if you can get a parallax, the distance to a star, and you know the back end of, have you ever looked at the back end of a telescope? The detectors? Your cell phone has got the same kind of a detector as they put in the Hubble Space Telescope, or very similar, okay? And all these big fancy telescopes, except theirs are really, really high quality stuff, okay? So they're called charge-coupled devices, all right? So when they get hit by a photon of light, it goes bing, just like your retina in your eye. And then it translates to a little bit of voltage, and then it, you know, your phone or the satellite puts it all together into a JPEG, and you know, and your brain puts it all together into this incredible moving movie that never stops as long as your eyes are open. Anyway, so if you have that, if you get the luminosity, the back end of the telescope is going to read 22 microvolts. Okay, that's a little bit of electrical voltage. All right, so it's really dim. Starlight is really dim. But if you also know the distance, you can figure out, okay, how bright is it at the surface? If you know the distance, you can do that. All right? Now, here's an example. Now, it's not in the notes, but I want to go over this with you. If you have a 60-watt bulb, and and the 60-watt bulb is over by this marker board, okay? The 60-watt bulb is over there. It's about 15 feet away from me, and it's not going to blind my eyeballs, okay? It's going to be nice. I mean, I might be able to read by it or something. If I get a little bit closer, maybe I'll be able to read by it. But now if I bring that 60-watt bulb and bring it right up here to my face, it's going to burn my eyes out. All right? So the whole idea of a single light source being able to read by it or burning your eyeballs out with it depends on the distance. Let me repeat that. A single light source, whether it's a star, the moon, a light bulb, the difference between being able to read by it and burning your eyes out with it is distance. Okay, the closer, the more danger you have of getting your eyeballs burned out. Okay? The further away it is, it's going to dim out and it's not going to be painful, and then you'll be able to but on bright night, the full moon, we got a pretty close to a full moon right now. You can read a newspaper. If it's a clear night tonight, you go out there and read a newspaper, or don't use your phone because that's got its own light source. But take something inanimate like a book or a newspaper. You can read it. You can study at night if it's a full moon. All right? Cast shadows, everything. All right? And that's because the moon is close enough and reflects enough sunlight from its surface to us that we can read by it. But now, here's something that they may have told you guys at the observatory. Never look at the full moon with binoculars or a regular telescope. Only look at it if you have a good filter. Because the moon is so bright that if you look at it with the full moon with binoculars or like a spotting scope, if you're a hunter, you look at a full moon, that's like dilating your pupils to the opening at the front of the binoculars. So that's like right now your eyeballs have a few millimeters of opening. The iris is open a few millimeters. But if you use a binocular, the whole idea of a binocular is brighten things up and bring them closer. And the bigger the front opening is of the binocular, the dimmer the object is that you'll be able to see, because you're gathering a lot of light and you're focusing it down into the eyepiece that you look at. But if you're doing that with the moon, it will burn your retina. Same as the SUN. Now, nobody would look at the SUN through a binocular unless they were like, I don't even think anybody would actually do that. But even, like on a solar eclipse, you're not supposed to look at the sun because the X-rays and stuff can really harm your retina, unless you have really good filters and stuff. I wouldn't even do that. All right. So the whole thing here is to get the distance. So if you know how many square meters of surface you have, you figure out how far it is, you know how luminous it is, you figure out, all right, that means I've got so much luminosity, and I've got so many luminosities, so much watts per square meter. You can figure out how many square meters that you're looking at. And then you can figure out, all right, that tells me the radius of my sphere, 4 pi r squared. That's the area of the sphere. So you can figure out r. So you figure out the size. And that, my wonderful students, is how we know that Betelgeuse is not just a giant star, but a supergiant star. Betelgeuse, its radius would be out past the orbit of Jupiter, they figure. It's just really gigantic. It's fairly close to us, but it's red, so it's not really bright square meter for square meters, but it's just got a lot of square meters. In fact, it's supergiant. So let's review it here on our as an outline. Here's the surface logic again. Stars and other large objects show similar effects. Wien's law, lambda max times t equals the displacement constant. Stefan Boltzmann law, the flux is equal to sigma t to the fourth. And so you use the diffraction and a light meter to measure the wavelength of the brightest color. So you break it up, like with a prism or diffraction grating like we did in class. All right, and then you use a light meter to say, all right, is green, which of these greens is actually the brightest? All right, so you decide that. That's your lambda max. All right, and then you use Green's law to get the surface temperature, capital T. All right, and then you use Stefan Boltzmann to get the flux, and that's actually similar to what we call the solar constant. In other words, the solar constant is about 1370, around in there, watts per square meter that arrive at the top of our atmosphere from the SUN, all right, as I've mentioned before. But to do any of this, you've got to know the parallax. Okay, and so that's one of the reasons why astronomers spend a lot of time. It was hundreds of years. It wasn't until like 160 years ago or so, something like that, around the time of the Civil War, that astronomers could start getting parallax measurements, because they're the nearest stars are so small that it's really hard to get a parallax to them. But now we got spacecraft up there like Hipparcos, that was up in the 90s, and now we got this one called Gaia that's up there now, just measuring buku stars and getting them all. And when you put all these things together, you start to see patterns. All right? And those patterns are called spectral types. Now, here's a table of spectral types. And this is, again, something from the late 1800s, when they started, taking as many spectra as they could photographically. And they didn't know they didn't know the Wien displacement law at that time, the way we do now. So they had like this alphabetic system, and they had, A through Z, I guess. But they don't really use anything other than O, B, A, F, G, K, M. And those spectral types, and you can look at this up in the textbook, those are the spectral types that all stars fall into. All right? They all, and it's basically another way of rating the surface temperature. So a really hot star is going to be a type O. And this diagram here tells you that, this is the O-type star up here, and you can see certain spectral lines. That's what they were thinking of. But now we think of it as get that peak wavelength and get the surface temperature. So we know what the temperature of old-fashioned spectral type O is. We know what the average temperature is for old-fashioned spectral type B stars. And there's zillions of them. Every one of these spectral classes have, hundreds of stars that we've seen. These types, spectral types, are not used. You sometimes see R spectral type mentioned, but mostly it's O, B, A, F, G, K, M. Here's a close-up look, and this is a nice. You can see zillions of different versions of this chart. Spectral types, examples. Like O, spectral type O at the very top. Examples: the stars of Orion's belt. All right, that's what you guys were looking at last night. Temperature range above 30,000 Kelvin. All right. Key absorption line features, ionized helium and weak hydrogen lines. And you can see on this diagram over here, they have a kind of an indicator for hydrogen lines. Here's H alpha over here on the right, this vertical line. And then you go down to type M, and down here at the very bottom, Betelgeuse, Proxima Centauri. Proxima Centauri is a small red star that's fairly close to, it's the closest star to us right now. It's in the Alpha Centauri system. And this chart says that it's got less than 3,500 Kelvin for the temperature. All right, so Betelgeuse. Now, it says that the key absorption features are strong molecular lines. Okay, so look at that. Down here at the bottom, titanium oxide. You know what titanium oxide is? You know what we use that for? Sunscreen. White pigment. You know, a painter uses titanium oxide. We can see to the surface of the SUN. And here's some more titanium oxide lines over here. Now, spectral type tells us, the spectrum of a star tells us a lot more. The Doppler shift. Now, this is what I wanted to go over with you. The Doppler shift in spectral lines reveals velocity and even rotation. All right, now let's look at this diagram here. All right. This is kind of an idealized view of a blue star orbiting a red star. Okay. Now you're over here. This is you over here. And over here on the left, that's the blue star orbiting the big red star. Okay. Now we can tell that they're orbiting, even if we can't, if they're so far away, we can't see them apart from each other. If we see their spectra shifting periodically, then yeah, we'll see it. So here's what you look for. So here's like the H alpha absorption feature right here, this black line, okay? And that is when the star, that is different from this part of the orbit. When it's down here on this part of the orbit, the H alpha line is shifted deeper into the reds. So that means my good old H alpha, and there's the other H alphas are listed up there. You can analyze them the same way. So your H alpha, here's where it should be if you were stationary. You know, right in between your two observations. So H alpha in our lecture hall is right here. All right? That's the standard H alpha color. Now, if that planet is moving towards you at a certain amount of speed, it's going to be blue shifted. In other words, it's no longer the lab red. It's now a little bit more orangey. In other words, it's shifted toward the blue. All right? And you can measure that. If you measure the wavelength for a few minutes of the motion of this star, you can actually figure out using some formulas from relativity how fast it's moving. Same thing down here. You can figure out down here, this is a redshift. Look at this. Use your eyes up here. Eyes, eyeballs, eyeballs. Come on. All right. This line down here where my cursor is, that's shifted deeper into the reds because the star is moving away from you. You're over here, and on this part of its orbit, it's moving away from you. So it's a longer wavelength. It's a redshift, deeper into the reds. Right now, sometimes it's not this drastic. This is pretty fast motion. But you can actually figure out the speed. So here's your blue shift. Go ahead and make a sketch of this. Okay, there's your blue shift. So here's the central, here's the lab absorption line right here. Now, if this thing were just over there in the sky, not moving toward us or not moving away from us, that's where we'd see H alpha. But that blue star's got H alpha, and it's moving. So we see a blue shift here, and then down in this part of the orbit, we see a red shift. All right? Now, if you track the red shift, there it is. You can actually figure out the speeds. This is V subscript R. It's the radial velocity. We can figure out how many kilometers per second the star is moving away from us or toward us. And my wonderful students, sometimes this is all you can see. And here is an example. The spectroscopic binaries in Ursa Major. Did you guys look at the Big Dipper at all? Okay. There it is, Mizar. We can't break it apart. At least maybe the Hubble Space Telescope can now, or Gaia. But some stars are so far we can't break them apart. But we can still see the H alpha line. Deep red, orange, deep red, orange, deep red, orange, deep red, orange. We measure that shift every day, every hour, deep red, orange. And we find that it's got a companion star. I have 6 more slides, but no more time. So, HR diagram I wanted to get to HR diagram today. Will not be on the exam, but everything up to this slide will be. All right? It's 10:14 and 26 seconds. You're dismissed. Look for homework this weekend. I'll see you next Tuesday. You guys with questions, come on up. Lights 100%, please. Hey.
I was just curious what chapters I should be studying.